Okay, so here we're going to take a look at just the structures of graphs here and in a special relationship that we can define between two graphs. So we'll start with this example, and we want to ask ourselves, are the graphs below equal, right? Where we can describe a graph as two sets. First set being the set of vertices, and the second one being the set of edges, right, which are these pairs, right, that are unordered, right? AB, edge AB is the same as set BA, right? Or not directed. Okay. So here, if we look at, well, we have the same number of vertices, right? We even labeled them the same here. But we could see here that the edges aren't exactly the same, right? So we would say, well, maybe they're not equal in the sense of their naming being the same, right? And right, that won't be true, right? That is true, I mean, right? So not equal in that sense, but it does bring up just a bigger point here. Well, maybe we're not after equality, right? If I draw these graphs, right, one possible version of these graphs are the graphs that look like this. Okay, and we could say that they're not equal in the sense that, right, we don't have edge AB, here we have AC, here we have BC, and here we have CB, right? So that one edge kind of doesn't have in common, right? But visually looking at it, says, well, this looks very similar, except for really the naming of the vertices, right? So we have a special name for these types of graphs, right, which will define, right, where they're basically the same, except maybe for the name of the vertices, right? So maybe we need to redefine them. Uh, and in doing so, right, we can do that via a function, right, where we relate the vertices in one graph to the vertices in the other. Right now, how we do this, so here let me bring up a definition here from our textbook. So when two graphs are the same, really, except for the name of the vertices, right, these are what called we call an isomorphism, right, where they're basically the same, right? So here's the definition, right? It says an isomorphism between two graphs, G1 and G2, is a bijection, F V1 onto V2, between the vertices of the graph such that AB is an edge in G1, if and only if, right? Again, definition, F of A, F of B is an edge in G2. If two graphs are isomorphic, if there is an isomorphism between them, in this case we write G1, and that little symbol here will define as isomorphism is isomorphic to G2. Okay, so again here redefining that symbol when talking about graphs. Okay, all right, now how to determine whether two graphs are isomorphisms? Well, it could be challenging, but here's some things that we can do here. Just some things to keep in mind here. So it can be challenging to show that they are isomorphic, but it might be easier to go through the route of trying to show that they are not isomorphic, that there's something that is that they don't follow with some of the properties of them being isomorphic. Right now, again, keep in mind via the definition, right, we're able to define some function here from V1 onto V2, right, on the vertices, right, on our first set, which we call a bijection. Now, again, bijection here, a reminder what that means is that here, not only is it one-to-one, right, but every element in the domain has to go to, well, another element there, and as a whole, all the elements in the domain, right, cover essentially the elements in the codomain, right? So here, if there's three elements here, then these point to an element each in the codomain, and there are no other elements, right? Because keep in mind that here a function like this, this is a one-to-one function, right? But it's not what we call a bijection because it does not cover the whole domain, right? So when we say bijection, we mean that all of the vertices are mapped on into the other vertices and that those edges line up, right? Now, some properties of isomorphisms to keep in mind is that they have, because of this bijection that's required, we need to have the same number of vertices, right? Same number of edges. And the degrees of the vertices must be the same. Right? So these properties here, right, need to be preserved because of that one-to-one correspondence. Okay, so if one way to go about where you're like, okay, is this an isomorphism? Well, maybe we start with trying to see if maybe it's not, right, by seeing if any of these properties hold, or excuse me, any of these properties fail. Right, so let's go through let's do two examples, one where we do have an isomorphism and another where it's not, and how to recognize that, without, you know, putting in, without having to try to create some bijection where there won't be one here, right? So let's take a look at two graphs. All right, let's take a look at the graph G, which I will define in this manner, right? G consists of the vertices, which I'll call U1, U2, U3, U4. And then, so this one is G. And then a graph H, where H consists of the vertices V1, V2, V3, V4, and connected in this manner here. Okay. All right. So here, let's list off here. G consists of, right, the vertices U1, U2, U3, U4. And then the edges U1, U2, U2, U4. U4, U3, and U3, U1. And then I'll call this one graph H. So H consists of the vertices V1, V2, V3, V4, V1, V4, V2, V3, V1, V3, and V2, V4. Okay, so we see that they have the same number of vertices. All right, that's great. All right, at least that leads us to see that there may be a possible isomorphism. Right? We also see that they have the same number of edges, right? 4 edges in this case. And the degrees also match up, right? Each one of these vertices is of degree 2. Each one of these is of degree 2 as well. So at least that is preserved, right? Now, again, that is not enough for it to be an isomorphism, right? But it does tell me that, all right, we're on the right track. All these properties are preserved here. So now it's up to us, we actually find this bijection, right? Where we go, so we need to define the function f right? Where this is our V1, this is our V2. Okay, and then here, so let's start by, all right, what if I set up F1 to be V1, F of U2 to be V4, right? And here, we could see kind of the connection here, why I would want that. And F of U3 to be V3. And then F of U4 to be V2. All right, and now let's take a look at the four edges here in graph G. All right, so in graph G, we have our edges to be U1, U2. Right, and then if I look at F of U1, F of U2, how I define these, we would have V1, V4, which just does check off right there, right? Okay, and then here, let's take a look at another edge. We have U2, U4, right? And then through our function, that would be F of U2, F of U4, and that would be the corresponding edge V4, V2. And we see that's right there. Right? Okay, and then here, the next edge going along here, we got U4, U3, right? So F of U4, F of U3. And we can see here that corresponds to F of U4 we define to be V2 and F of U3 to be V3. And we see that edge is also there as well. So far so good, right? And then lastly here, we have U3, U1. Right? And that maps onto F of U3, F of U1. And that is V3, V3, V1. We can see that is right there. So here we go. We created the bijection from V1 to V2, right? And that tells me that graph G and H are isomorphic to each other. Okay. All right. So let's take a look. Let's take a look at another example. Right. So let's say we have a graph that consists of here, A. So A, B, C, D, and E. Okay, and then here we have here. Okay, and then our next graph would be defined by similar A, B, C, and D, and E. All right, now for this one we could see here, all right, we have the same number of vertices. So okay, nice start here. We also looks like We have the same number of edges. Okay, so far so good, right? Again, just because they doesn't look the same here, right? And the names of the vertices are those are the same, but they don't look the same, doesn't necessarily disqualify it to be an isomorphism, right? As long as we can rename them in a certain way to generate that bijection, then it's fine. Then it would be isomorphic, right? So far so good. Same number of vertices, same number of edges, right? The only thing here, when I look at this, we say, all right, well, is the degrees preserved between the two graphs, right? And well, here's where we have an issue here, right? Where I don't need to actually go any further to prove that that it is a bijection. Because if we look at here, let me label this graph G and graph H. In graph H, the degree of E is 1, right? Only one edge is going into it. Well, if I look at my other graph G, nowhere there does a vertex have a degree 1. All right, at minimum, it has every vertex has a degree 2 or greater. So I know that that will not be preserved in our one-to-one correspondence, so I cannot have a bijection. So here, G is not isomorphic to H. Okay, so again, like I said, sometimes not sometimes, it can be challenging to create this bijection or to determine if they're isomorphisms. And also, it's good to just kind of go through these properties that need to be preserved, right? By definition, this has to hold, right? So we'll go through that direction to determine whether a graph is isomorphic or not.